All right, welcome back. In this session, we're going to be talking about connections and more specifically groups of bolts that are loaded in eccentric shear. Okay, and in particular, there are lots of methods for analyzing this, but we're going to be turning our attention to the elastic vector method, which is, for the first time out, is a fairly simple method to conceptually understand what's going on. And so we will pursue our studies into that area. All right. So here's the definition of an eccentric connection. All right. Before we had a case where we had two plates bolted together and then I was putting a simple shear force on them, but never did we have any sort of rotational effect. This one's a little bit different. Okay. So what I have is I have a bolt pattern and the circles represent the bolts. In this case, I have, 3 rows and 2 columns of bolts on this. And what I've done is I've loaded this connection eccentrically to the center of the group, which means that there's some what we call as an E value here in which I put a load out at some point. Okay, and in this particular case, I'm going to say that it's 24 kips. And so the basic method looks something kind of like this. If I know the spacing of the bolts, and for purposes of this exercise, we'll assume that everything is equal, that the gauge distance is 3 inches between bolt lines, and then it's a 4-inch spacing for this. We want to be able to figure out, for a given size of bolt, is this connection okay? Okay, and what this does, this allows us to start getting into a study of how do we determine if an arrangement is good. This is the connection detailing portion of our study. But the basic idea behind an eccentric connection is that I can turn this into 2 cases that I can develop a methodology to be able to resolve. Okay, so the first case that you see here is the direct shear method, and this is the one that we've talked about already, in which I have just a simple force that's located through the center of the bolt pattern. And what will happen is that each of the bolts, as we look at it, will be subjected to an equal portion of the shear. In fact, I know that the shear across this bolt due to this load is shared equally, so it will be this load divided by the number of bolts, and it's the same across all of them regardless of the pattern. Okay, the one that gets a little bit different and makes things a little bit more complex for analyzing is the second half of the equation. All right, so by moving this force back from static, back to the center of the pattern from statics to get us the case that we know how to analyze from before, I do introduce a moment into the connection. Okay, and this is the rotational characteristic of what's happening. And so this whole plate is wanting to spin about that same center point of the pattern. Okay, and when I do that, okay, each bolt works a little bit differently to provide that moment, or to be able to resist that effect. And so in this case, the top upper bolt, if I number these as 1, 2, 3, 4, 5, and 6, the first R1 develops a shear force across the bolt, but it's no longer vertical or horizontal. In fact, if I look at relative to the center line, that's 90 degrees. All right. And it's the same for all of them. Every one of these, the force develops at a perpendicular distance. That's how we develop the moment around that center point. Okay, and so you can see that this guy will have a little bit of a component that's horizontal and a little bit that's vertical, and this guy will have a little bit horizontal and a little bit that's vertical. But notice the directions are different. Okay, they're both contributing to that total moment in the same direction, relative to this point. If I take this line and bring it back over here, we're contributing the same. So based on the position of the bolt from the position of the center of the pattern, I can start to anticipate the moment that develops. And then all of these 6 in this pattern, or however many bolts you have, but the 6 that are in this particular one, all of these added together, okay, will be equal to that applied moment that we have. Okay, so it's just a matter of being able to kind of break this down into bite-sized pieces. Okay, now from a design standpoint, a couple of things that we know. Okay, is that we're going to say that each bolt has its own pair of coordinates. So for bolt number 1, he'll have coordinates of x1, y1. Okay, and then we will measure the distance. That if this is the center of the pattern on here, then and this is the coordinates of x1, y1, then we're going to define x as the difference between his center point and the center point of the pattern, and then y will be the distance between his center point and the center of the pattern in the y direction, all right? So you'll use your basic statics or centroid calculations to find those locations, and then I can plug in the coordinates of my bolt and come up with those parameters. And these parameters will be important in our calculation as we start to kind of look at all of this. All right, so here are the formulas that we're going to need to be able to analyze this problem mathematically, all right? Okay, so if we go back and we look, okay, if you remember on our basic graphic up here, we defined E as being the distance from the center line to the load. Okay, and so again, the center line is the point that passes through the point, okay, and this center line is parallel to the direction of the load. So if I have a horizontal load, then my center line would be a horizontal line through that center point. If I have an angled load, then it will be an angled line coming down through the center point. But the E is that perpendicular distance. Again, we're looking to try to convert this into a moment. Okay, all right, so just keep in mind that that's what E is. All right, so the E that we're going to analyze in, for our particular case, we said that we had, it was a 3-inch spacing from the edge of the bolt plus half of the 4-inch pattern. So if we flip back up here, so we'll notice that the load, center line of the load was measured 3 inches from the front row of the bolts. Okay, and then this pattern, because it's regular, would be located, the center point would be located at halfway through the middle. Now that may or may not be the case depending on the arrangement of the bolts, but you can find that point, we can conclude it, but that's how I'm kind of computing the E value. Okay, once I do that, then I know that my E is 5 inches, okay? All right, now, again, just kind of as a reminder, you can find the center of the patterns by just simply taking the coordinates, the x coordinate of every bolt multiplied by the area of that corresponding bolt divided by the total area of all the bolts in the pattern. That will get me the x bar, that center point coordinate. Okay, and then the y bar is the same thing, only using the y. Now, notice what we're doing in this is that what I recommend as you start to kind of look, you know, if you have a bolt pattern, you know, in our case that has, you know, multiple bolts on this, you know, typically what I'll do is I will set the origin as being the lower left. Okay, and when I do that, what that does is it makes sure that my x and my y coordinates for all of these are always either 0 or some positive value, and then I don't get bogged down in some sign convention errors, right? So, and so then for finding these centers, these x bar and y bars, then I know that that's x bar, and I know that this is y bar as we start to kind of look at those. So that's one little tip that we'll make on setting all of this up. Okay, so once I've got x bar and y bar figured out and I know what my E is, you know, because I do need E to get this guy, that has to do with that x bar. Okay, all right, then I can calculate what that second piece of the puzzle was. You know, like I say, the direct shear case we knew how to handle. It was this guy that was different. So the moment that's created is equal to the load that I had, PU, multiplied by that eccentricity value that we just found. And that will give me a measure of the amount of the moment that has to be occurring on that second part of the problem. All right, and that's what we do. So MU is equal to PU times E, okay, and that's 24 kips times 5 inches is going to be 120 kip inches a moment that we have to be able to account for. Okay, all right, so that's the second piece of the puzzle. The third piece of the puzzle, it may not be completely obvious, but what it is remember we said that the moment capacity of that eccentric portion was based on perpendicular distances to the forces acting across the bolts. Okay, and then we're going to sum all of that together. Well, behind the scenes, what the method does is it computes a quantity that is the sum of x squared plus the sum of y squared for all of the bolts. All right, and so what we can do is we can go in and we can look, and these are kind of in kind of an odd order, but if we look, we can see that for bolts 1, 2, and 3, and then 4, 5, and 6 on there, that 1, 2, and 3 are located at what would be a -2 from the centroid. So their x value is -2, assuming the centroid is 0. And 4, 5, and 6 would be a +2. And then likewise, the 1 and 4 bolt will be at a +3 if we assume the centroid is 0. So +3, +3, and then 2 and 3 in this pattern, because they're on the same line as the centroid, will both be 0, and then 3 and 6 will both be -3. Okay, so they're all relative dimensions that kind of come back to that picture that we were drawing here. Okay, all right, so when I do that, I can calculate this quantity, this sum of x squared plus the sum of y squared quantity. And so you can see, so this was bolt number 1, this is bolt number 2, this is bolt number 3, this is bolt number 1, this is bolt number 2, this is bolt number 3. So the first set here are all my sum of x squared terms, okay, and then the second batch here are all of my sum of y squared terms. So bolt number 1 was at -2, and then it was up at +3. Bolt 2 was -2 and 0, and bolt 3 was -2, -3. Okay, and so that's all we're doing is building the coordinates. And then likewise, you can do the same thing for 4, 5, and 6. 4 is +2, +3. 3 is +2, 0, and then, or sorry, 5 is +2, 0, and then 6 is +2, -3. And so you can see all of those terms showing up in the mathematics of this equation. So it's a very easy calculation that we're doing here. Okay, and if I do the math on all of this, I'll find out that this summation is now 60 inches squared. Okay, so no major issues on this. Okay, now all we're going to do is we're going to set up for each bolt. We're going to find the eccentric shear components that are existing. So let's just say that we grabbed one at random. Okay, and in this case, I think I took bolt number 4. So if you remember, bolt number 4 was the one on the upper right. So we had 1, 2, 3. We're looking at this guy right there. Okay, and you'll do the same process for everything. But basically, I knew that force was inclined at an angle. Okay, and to make the moment relative to the centroid that was here in the middle. Okay, and so this force I know has an x component and it has a y component. All right, so what we can do is we can figure out the x component by simply taking that moment, multiplying it by the y coordinate, that should be the y4 coordinate, okay, and then all over that summation that we just found. So the x component of the force in this guy is 120 times 3 divided by 60, or it's a +6 kips. Okay, and the positive sign indicates that it's acting to the right, which is what we would expect on this one. Okay, and then Ry is a very similar formula where it's the moment times x4, okay, over that summation that we had. Okay, but there is one difference, okay, and that's that minus sign that's acting in front. You need that to get your signs squared away so that the directions all work out. The hardest part of this method is getting those signs, and most often the mistake that's made is leaving off that minus sign on here. Okay, and so for all of these then, we can calculate minus 120 kip inches, okay, times a +2 inches over 60. So again, this is not the coordinate of the bolt, it's the distance of the bolt. So it's basically that, that y4 minus y bar value, and sorry, that was an x4 minus an x bar value. Let's fix that real quick. So it's the center of the bolt, 4 minus x bar, and then this guy was y4 minus y bar up there. Okay, so it's just basically setting yourself up for that. So this is the difference that we had, okay, where we're assuming that y bar and x bar are the coordinates measured from the centroid. All right, okay. All right, so once we've got that, then I can do my math on this guy, and we find out that it's -4 kips, and it's a negative sign acting downward. Okay, and that kind of jives with what we would expect on this. And that's how I calibrated the signs on this, was to make sure that it got me the directions that I was expecting. All right, and so we just repeat this process for every bolt. We calculate these quantities. All right, once you have these two components, what you can do is you can now find the resultant of all of these, and we'll do that here in just a second, a little bit later on. Okay. But the resultant force from the eccentric shear case that's happening up here is quite manageable for us for there. Okay. The other piece of the puzzle for bolt number 4 is calculating the direct shear components. All right. So if I have my bolt and it's, and again, we're looking at for number 4 again, we said that there is some shear, and then I put a subscript of y on this to indicate that it's in the y direction, but that was because my force was in the y direction. All right, and so we can calculate this quantity by taking RVy over that applied load, his y component, divided by n, where n is the number of bolts in the pattern. So if I had 6 bolts in the pattern, that's why there's a 6 here. Okay, and so again, it's a negative because it's acting downward. And so it's -24 kips over 6 is a -4 kips, or 4 kips acting downward. So with that, I now have the 2 parts of the picture that I need. Okay, and so now it's just a matter of putting all of these pieces together, and this is how you do it. My page is sorted here a little bit. Okay, all right, so here's what we're going to do. Okay, so all we're going to do is just do a simple superposition. I'm going to take the direct case, that I had, and we said that was a -4 kips acting on this bolt. And I'm going to take the eccentric case, which is going to be the x and the y's that we saw from the moment case. And so I had -4 acting down, and I had +6 acting to the right. All right, so if I add all those together, and again, this is an elastic vector method, so we're still assuming linear elastic isotropic homogeneous behavior, okay, that nothing is deforming locally, that everything is static and able to withstand the loads. Okay, and so for bolt 4 then, when I add these two together, I get a -4 plus another -4 gives me a total of -8. Okay, and then I take 0 on this guy plus 6 on that one gets me to +6. Okay, and so the total is -8 down and 6 to the right. All right, and so with that, I can now go in and I can find the resultant force of the entire system just by simply adding these pictures together. Okay, and so all I'm going to do is I'm going to take the square of each of these terms. So I'm going to take -8 squared plus 6 squared and then take the square root, and the magnitude of the force on the bolt is now 10 kips. And that's all there is to it. Okay? All right. So for bolt 1, which again, if these were my 4, was this guy here, we knew his force was acting this way. What happens is it's a little bit differently, right? The direct shear on this is still -4 kips. Okay, that's the same for everybody in the pattern. Okay, the one that's different now is that his direction on this 4 due to the moment is different. All right, because that x parameter was a negative back up in this equation, that minus sign is going to flip his direction. Okay, and when I do that, so his component acting up, would be an upward force of 4 kips. And then, of course, the horizontal is still the same because that was the same line as what I had. So if you look, this force is from the lower left to the upper right. That's what you're seeing. It's this guy. It's the same thing, right? So then I just combine the two like we did before. And so the forces on the combined bolt then is a net effect of 0 acting on this bolt and to the right of 6 kips. All right, so then when I go and I find the resultant force on this one, square root of 0 squared plus 6 squared is just 6. And so you can see that that upper right bolt number 4, has a lot more force than the bolt on the upper left because of the eccentricity and the fact that these two 4 kip guys were starting to fight each other. All right. All right. Now, if we go back and we and so you can repeat this process for all of the bolts. All right. So if we go and we kind of look at the entire pattern, we can kind of do the superposition of these. Now we did all of these. This was number 1. This was number 4. Here's number 2. Here's number 3. Whoops, sorry, that's number 5. Here, this is number 3, and that's number 6 for the bolts that are in our pattern. Okay, and so these were the cases that we were seeing, and this is what it kind of looks like as we're starting to combine things for a load that was out here somewhere doing, a PU kind of thing at some eccentricity from the center of the pattern. All right, so again, this distance we said was an E of 5 inches. Okay, and so for that particular eccentricity, you can kind of start to see if you plug in the equations, you will see that this set of bolts actually has no horizontal force. Okay, because it's concentric to this point. There's no eccentricity relative to this. So the line horizontal line through this is passing through that. So there's no perpendicular distance. So there's no moment caused by the horizontal. But there is a vertical effect of it. So RV is the same for all 6 of these guys. Okay, and then you'll notice that to the left of the centroid, my RY, which is from the moment, the eccentricity due to that eccentric force, that they're all acting up on this side. Okay, and so you can see that for this case, typically these bolts will have a smaller magnitude because the direct shear and the eccentric shear portion of this are fighting each other and actually reducing the overall quantity, and that reduces the magnitude of this force. Whereas on the other side, on 4, 5, and 6, I get a horizontal, this horizontal and this horizontal will be the same. Just like this horizontal and this horizontal will be the same. Like this horizontal and this horizontal will be the same. Okay, but the direct shear is still RV, but then that eccentric shear portion contributes in the same direction. So we're kind of looking at the signs of the arrows on this, that it adds to RV on both cases on this. So what happens is relative to eccentric shear, the forces in the bolts on a pattern of bolts become much larger if the bolt is between the centroid and the load, whereas the ones on the backside aren't having to work as much because they're starting to counterbalance the direct shear forces. Okay, so that's kind of one thing that can kind of help you reason your way through. Now, this is a fairly simple example with just six bolts, but you could do this for 8 or for 10 or for 12 or however many, right? And one thing I have a spreadsheet that I use fairly regularly that I can put up to 16 bolts in a pattern, and I can locate them in any x1, x2 coordinate. All I have to do is figure out where is this location for every pattern, and that's a pretty trivial possibility if you know the size of the bolt that you're wanting to use and you're knowing the location or the arrangement of the pattern. It's a very, very easy calculation. So this is a very, very handy tool, and one that I'll have my advanced design student classes, students in my advanced design class, I'll have them make this one. So this is a good one to have, if you're out practicing, just as a kind of a quick and dirty calculation for that. So that's basically it for the elastic vector method for calculating eccentric shear capacities for connections. All right. So what we're after in this a lot of times is, maybe I know the bolt size and the location, what's the maximum load that I can put on this? And so this is it's almost kind of like a load rating kind of calculation. But what will happen is when I do a design, I will do this at the end just to kind of, when I start working on the arrangement of the bolts, to come up with the most compact, most efficient section, because this layout shouldn't ever control the design, structurally speaking. If my beams and columns are sized right, I should be able to design a connection or lay out a connection. And, if I have a problem where I can't hold the load that I think I need, all I have to do is change the spacings of the bolts or even change the bolt size, and I can get drastic increases in the capacity of this. So this is always kind of an after check, when you're doing the connection design, and not when you're doing the upfront, structural member calculations like we've been doing up to this point. So AISC has a lot of tables that they utilize to kind of shortcut this method a little bit, and I'll walk you through that here in just a second. But for now, the elastic vector method is very, very handy. It is conservative. It will overestimate, or it will underestimate the amount of load that's on the connection, or it will require a larger bolt size. But a little bit of conservative isn't bad. But it's used mainly to get you an idea of, is this connection possible, or is it going to get me the capacities that I think that it needs? And for that, I still think it's a very valuable tool. And especially if you have a spreadsheet, you can just punch some numbers in real quick to just kind of get a sense or a feel of whether or not your design is headed in the right direction before you do the final calculations. There's some other methods out there. There's an ultimate strength method, which takes into account the deformation, which is kind of beyond the scope of this, but they relax the criteria that nothing can deform, but if this connection deforms, this point starts to kind of move. But again, that's kind of beyond the scope of what we're looking at. So if you ever come across a calculation and mention something about an instantaneous center, know that is not the elastic vector method. So, all right, okay. All right, so we just got through talking about the eccentric shear calculations using the elastic vector method, but I wanted to spend a couple minutes and kind of walk you through some of the more useful features of the AISC design table. So I'm going to show you how quickly we can kind of work our way through this methodology. I've changed the connection a little bit. It's still similar, but for this particular example, I've now got 4 bolts in a line. Okay, and really the number of bolts in a line don't really matter, but the number of lines is a major factor on this. And so what I've done is I put a load PU at a distance of 6 inches, okay, from the center of the pattern, and then I have a pattern that is 3 inches by 3 inches on spacings in both directions, and then I've got a half-inch plate on this, because once I have the forces in the bolts, I can then go in and start doing our bearing calculations on the plate itself to make sure that we don't have any issues with the bolts wanting to plow through the connection or to try to rip through or anything like that. Okay, given in this example, the angle of our load we're going to declare as 0 degrees. Okay, this is an important parameter because the tables are set up, and I'll show you those, but we're going to measure that angle from the vertical direction in all cases. Okay, and then for us to be able to do this, we're going to assume that vertical spacings and the horizontal spacings are all similar. Okay, All right, now we're going to also assume that our bolt size is 7/8 inch A325 N bolts. Threads are included on this, and what we want to find is what's the maximum load of PU that can be put onto this connection. And this is where the AISC tables are really handy. Okay, so here's what we're going to do. Okay, the parameters that we need to be able to conclude from this is I need to know the number of rows of bolts, I need to know the number of columns of bolts, and I need to know the orientation of the load. Okay, so for us, if we come in and we look on this, in the 15th edition manual, what I have is I have a whole bunch of tables on here, and we're looking at the groups of these. So this is the actual table that we need for the problem that we're going to solve, but I want to show you some of the others first. So I have, if you look at the pattern here, as compared to the one that's over on this side, this is one column of bolts, and again, we're not worried about the number of bolts on this. Okay, but for now, I've got two columns of bolts with the load that is vertical. And then if I look over on this one, you can see now the next table is two columns of bolts with the load inclined 15 degrees and then 30 degrees. And you can start to see all of these and see how the load changes, and these coefficients that come out of the table will change based off of those. And then you can get into, let's see, we're still varying. Here we've got, three columns of bolts. And so the patterns change and continuously, and I went too far. It even goes up to four columns of bolts to be able to work on all these. So if I go back to our page, which was 737, okay, and we can start to kind of show you how we're going to start to use this particular table. The parameters that you see in the AISC, and it's a fairly easy calculation. And again, I apologize, it's a little blurry, but you can see the formulas. Every value that's in this is basically, it's a coefficient that happens here, okay? That's basically equal to, the coefficient is our capacity of the bolt over the load, and then this is our C minimum value that will come out of here. Okay, or they can rearrange this and say that this is the capacity of the connection, or the applied load is equal to the C coefficient out of the table multiplied by the strength of one bolt. Okay, and so we can kind of see those. But that's all we're going to do, is we're going to look at the way these tables are lined up. So the tables are broken up into a couple of categories. Okay, the first column that we have here is the spacing between the bolts. Okay, and they do a pretty good job of outlining what's S. So S in this case is the vertical spacing between the rows. Okay, notice that they've preset that the spacing between the columns has to be 3 inches. So you got to kind of watch that and make sure you get into the right tables on this. Okay, so S becomes an input parameter, and they've tallied up these for two fairly standard spacings. 3 inches is probably the most common, but they also do it for 6 on those. Okay, so all I do then is I figure out, am I a 3 inch or a 6 inch spacing between the rows? And then I come in and I calculate my E value, my eccentricity of the load, which is what we did in the last example. Okay, and again, if you look at the picture, EX is the distance from the load back to the centroid of the pattern on here. That if once I know this EX value, I just simply read down and I pull off this value, and then I read over based off of the number of bolts in one vertical row. So am I a single bolt? Am I 2 bolts, 3 bolts, all the way up to 12? So I can handle, my 2x4 case fairly easily by coming into the 4 and then reading off at my eccentricity, which was what value? If we look at our example here, if we look, it's a 3 inch spacing. We said 6 inches to the center, so we're at an eccentricity of 6 inches. Okay, so if we look at this, so I found the right table, 4 rows, 2 columns, load vertical. That was the table we're looking at. And then I take my eccentricity of 6. That's from the load to the center of the pattern. Okay, my spacing, my S value is 3 on there, and all I'm going to do is basically find my 3S, go to my eccentricity of 6 line, and I'm going to come down on my N equals 4 and find a number of 3.69. Right, hopefully. Okay, so if we look, get this up here, I'm coming down to the 4, I'm coming over on the 6, and there's the 3.69 value that we're pulling. That's all there is to this. Okay, once I've got that, we can put the book away, and we can come back in and do the rest of the calculation as such. Okay, so the table said, all I'm doing is saying that the applied load, this VRN value, was that C coefficient that we found, okay, multiplied by the capacity of a single bolt of my phi RN for my single bolt. And that R is a little faint. So, okay, so all I'm going to do is I'm going to take that 3.69. I'm going to multiply this. This is from table 7.1, which is the shear capacity of the bolt, and this is per bolt on that. And so 3.69 times 24.3 gets me to a 75.3 kips. And that's it. That's all there is to being able to use these tables for eccentric bolt patterns. Very, very easy, very, very quick. So if you don't want to do the elastic vector method, you don't have, and your arrangement of bolt patterns are fairly standard with a 3-inch or a 6-inch spacing, this is a good option for you to be able to quickly get in and get a value. But if we go back to our bolt pattern and come up with an irregular pattern, maybe this one bolt is off for some reason, or you're adding on to an existing connection. There's a whole slew of reasons why there might be different, a different arrangement. Then you have to have another method in your pocket, such as the elastic vector method, or a spreadsheet that helps you with those calculations to be able to help you. So that's why I like to present both of these methodologies for you. But when things are regular, man, AISC, it's like a 2-line problem, really, right? I write down my assumptions, find the right table, pull off C, and boom, we're done. Okay, so anyway, that's kind of how the AISC tables work. They're very, very simple, very, very easy to use. So this is just the beginnings of a lot of study and work that can be done into the areas of connections, and we're keeping it fairly simple at this point. But for now, we'll go ahead and we'll stop our discussion for eccentric connections, eccentric bolted connections here. So I hope this has been pretty clear for you. As always, if you'll leave, some feedback or comments on what we can do differently or better in the bottom of in the comment section below at the bottom below the video, we would greatly appreciate it. Please remember to like and subscribe to our channel, and we will keep the content coming, hopefully. So hope you all have a great afternoon. Happy engineering.